Okay, in preparation for our final, I'm just going to go over a couple different problems from the last couple units. These are quizzes I give to my in-person Stat 1350 students. So don't worry that it says quiz and there's points associated with it. They're just good problems to help you get ready for your exam. Obviously, look at the big exam review on Blackboard, but these will just be more problems for you to practice. So this first kind of video is on just the probability stuff, the Unit 8, Lessons 3 and 4 about simulation and expected value, where we're assigning digits and then trying to see what would happen. So this example says a field goal kicker on a local football team makes 63% of their field goal attempts. It says, how could you assign random numbers to simulate the making or missing of a field goal? So there's only two things that can happen. I'm either going to make a field goal or I'm going to miss a field goal. And so making a field goal happens 63% of the time. So I would like to make sure that 63% of the numbers I assign are making. And then that means 37% are going to be missing because 100% minus 63 is 37. Now, in general, you can either assign 1 digit, 2 digit, 3 digit. Now, if you assign 1 digit, you have to be in increments of 10%, because if I think of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'll put it down here, then there are 10 digits, so each one would represent 10%. In this case, I have 63%, so there's no way I can do it with 1 digit, so I'll have to do 2 digits. So if I do 2 digits, I want to assign 63 different numbers that are 2 digits to making a field goal. So usually we start with 0, 0. You can really start anywhere, but generally we just start with 0, 0, 0, 1, 0, 2, 0, 3. So I'm going to keep listing numbers until I have 63 numbers. So I'm not going to keep writing them out, so I'm going to go 61, and then 62 will be my last number. The reason 62 is my last number and not 63, if I go 1 to 63, it would be 63, but because I have this 0, 0, that's an extra number. So 1 to 62 is 62 numbers plus the 0, 0. So those 63 numbers will represent make. So the rest of the numbers would have to represent miss. So that would be 63, 64, 65, so on and so forth, all the way until we get to 98 and 99. So now we have all the digits assigned for make and miss. You can have events that have more than 2 things. On the review, you'll see like colors of different things, and there's lots of different colors. So you don't have to have just 2. You can have lots. So the second question that kind of goes along with this says, in the above example, using line 120, which is shown below, how many field goals will be attempted before we miss a field goal? So we're doing these in increments of 2. So the first 2 digits are 35. Now 35 is in this first column. It's in the make column. So this is going to be a make. The next 2-digit number is 47. 47 is in the first, so that's going to be a make. The next one is a 65, so that's going to be a miss. So it says, how many field goals will be attempted before you miss a field goal? So I guess that would be 3 because we missed the third. Sometimes you've seen problems where they tell you to do the whole line and figure out how many misses you have or what's your percentage of misses. We can certainly do that as well. This problem just happened to see how many do you need to attempt before you miss one. So the other kind of probability we had, this was kind of lesson 4, was the expected value, where you're trying to find the average value of an outcome throughout some kind of event. So this one, I have a probability model for the number of children a family has is given below. So we have the number of children is 0, 1, 2, 3, and 4. These are just random numbers I came up with. So according to this model, you can't have 5 kids because it's not on this chart. So the first thing says, what is the missing probability? Okay. Well, I want to know what's the probability of having 4 children? Well, remember, all these probability distributions always add up to 1. So to find the missing probability, I will just simply take 1 minus 0.23 minus 0.3 minus 0.17 minus 0.25. Now, they don't have to be like this. You could certainly add them all up and then subtract. That's also a great way to do it. There are lots and lots of ways to do it. So when I do this, I get 0.05. And so now B says, what is the expected value number of children for a family to have? So again, if I keep looking at lots and lots and lots and lots of families from this probability model, what is the average number of children they would have? So again, probability works very poorly in the short run, but in the long run, if you keep looking over and over and over, the average value or the expected value is pretty predictable. So the expected value, if you recall, is we would take the outcomes times the probability for each one and add them up. So the expected value for this problem is 0 times 0.23 plus 1 times 0.3 plus 2 times 0.17 plus 3 times 0.25 plus 4 times 0.05. So you can just put this right in the calculator. I am literally just putting it in the calculator exactly as I see it right here. So I get 1.59, if you believe me. So 1.59 children. So if I keep looking at these families over and over and over again from this, hypothetical distribution, the average number of children in these families would be 1.59. So just a couple problems, just to kind of give you some idea of question types that you might see on the final, not guaranteed. We'll also do some problems later in the week about confidence intervals and significance testing.